The next thing I want to do is to prove. I mean, during the proof of the theorem of Zellerdetz, we already saw that Lyapunov exponents are somehow related to invariant measures. We had these invariant measures, that eta s and eta I, that were important to prove that the limit exists, and we are going to go deeper into that. I'm going to state a theorem, and then I will spend some time defining the words and defining and proving the theorem. But the theorem goes in the direction of saying that you can compute the Lyapunov exponents from invariant measures of the convenience system. So, in fact, there are two theorems. A theorem due to Le Drapier, which says that we can obtain, in the text I call that the representation theorem of representation of Lyapunov exponents. So the setting is the usual setting, F R D except that in what follows it will be very important to consider this is a linear cocycle. And it will be important to consider the projective cocycle associated to this linear cocycle, which is just the same, except that we look at the action of the matrix in projective space. So this represents the line, the vector line generated by V, and we just look at the action of A on lines. So this is a projective cocycle. Okay. We are considering mu, a probability measure on M, invariant under F. And I'm going to consider the set of measures, of probability measures, M, probability measure on the product that project down to mu, such that phi star of M is mu. Okay, so the picture, you have a product. You have a product, here is M, here is the projective space, and you consider measures M here, such that when you project them, you get mu. More precisely, what this means is that the measure of A times projective space, the measure of any set in this form, is equal to mu of A for every measurable A. this is the space of measures in the product that project down to mu. So the theorem says that for any invariant measure M that projects down to mu, for any measure here projecting down to mu, there exists J. So I have to recall a little bit more notation. This is the oscillated's flag. And the Lyapunov exponents. For any invariant measure that projects down to mu, there exists some J such that the integral such that the jth Lyapunov exponent is equal to the integral of phi dm, where phi is this function that already appeared. Phi goes from m to write it here. Phi is the expansion function. Goes from m to prd to r, and is defined by phi of x v equals logarithm of ax v divided by v. And the set of vectors x, v, such that v is in Vjx has full measure. So I have this product. It's very difficult to draw pictures because we don't have much dimension. So you have to use your imagination. But for any, what this is saying is that you take M PF invariants then there exists some J. You look here for each point X, you look at the corresponding subspace Vxj. This, of course, depends on your point. And this is saying that the sets that I've drawn here, there in orange, is where the measure M lives. I'm cheating a little bit because Vj is a subset. Bj is a subspace of Rd, but we may consider it's a little bit of an abuse of language, Bj to be a subset of projective space. Right? A linear subspace is formed by lines, so it can be seen as a subset of the projective space. That's the reason why here I have V and here I have the line that passes through V. So what this is saying is that for any measure invariant under the linear map, it lives exactly on some Vj. This set here has full measure. And if you integrate this function with respect to your measure, you get the Lyapunov exponent. Now I have to remember whether we are thinking that the system is ergodic, because lambda j depends on x. Yeah, I'm assuming here, assume that f mu is ergodic. And then, as we know, Lyapunov exponents are constant on orbits. If you have an ergodic system, any function that is constant on orbits is a constant, so this is a number. Okay? There's another thing that I didn't say yet. I'm assuming that this measure is ergodic. So here, I'm assuming that this is ergodic. So here's the first very intimate relation between invariant measures and Lyapunov exponents and oscillated subspaces. The invariant measures of this transformation, this one, the ergodic invariant measures of this transformation have the following property. They live on oscillated subspaces, on the elements of the oscillated flag. They give full measure to such a graph. This is the graph. This is the graph of x goes to Vxj. And if you integrate this function, very simple and natural function, if you integrate this function, you get one of the Lyapunov exponents. Okay? Now, of course, when you have this statement, you immediately think which Lyapunov exponents can be written in this way. Which ones? For which ones is it possible to find an invariant measure that allows you to compute the Lyapunov exponent in this way? And the answer is for all of them. So conversely, for every j, by the way, once I assume that the system is ergodic, the number k of elements of the flag is also constant, so I don't have to worry about that either. For every j, there exists some PF invariant measure such that satisfies this. Okay. Maybe it's good to look at a simple example, simple situation, to at least believe this statement, and then we'll give a proof. So here's a kind of an example. Suppose d equals 2, and the first exponent is strictly larger than the second. So, and lambda 1 is bigger than lambda 2. And as we know, lambda 1 is lambda plus, and lambda 2 is lambda minus. So what this means is that at each point, at almost every point, this is R2, at almost every point, we have R2, which is equal to V1, and then we have the next subspace in the flag, which is Vx2. Okay? Now, as I said, we may view this in projective space. This is the linear picture. Let's look at this in projective space. Well, projective space is just a circle. Well, the projective space of PR2 is just a circle. And this V1, I said that we may consider V2 as a subspace of projective space. Well, it's easy to see which subset this is. This is just the subset formed by a single point, the point where by this line, the point defined on the projective space by this line. Okay? This line is an element, it's a point in projective space. So here is Vx2 seen as a subset of PR2. But in my picture there are 2 points, but in projective space they are the same. The projective space is not really the circle, it's half the circle. Okay. So this is the picture that you have at each point x of M. At each point x of M, this is the picture that you have. And now the question, I stated a theorem, I'm going to prove it, but I want to give you one example where you can see that the statement is true. I want particularly to illustrate the second part. In a sense, the second part is more interesting because it says that every exponent can be computed in this way. So according to the second part of the theorem, there exists some PF invariant measure M such that that projects down to mu such that those two things happen. Phi of the integral of phi is lambda 2, and this measure gives full weight to this set. Okay? So I want to show you, I want to exhibit such a measure. In this simple situation. Which measure is that? So it has to be a measure in the product P of R2 mu. It has to be a measure here that projects down to mu. Now here comes the first information. Any measure that projects down to mu is of the form that the measure of a set is obtained. I'm going to explain this in the picture. The measure of a set D can be obtained in the following way. First, you measure the verticals. For each point x, you measure the verticals. And then you take all those numbers and you integrate with respect to mu. Okay? So it is an integral with respect to mu when you vary x of the measure in the vertical. The vertical, of course, is just D intersected with x times PR2. So any measure that projects down to mu can be calculated in this way. You calculate the measure of the different verticals, and then you integrate that with respect to mu. The one thing that I didn't say is how do you calculate the measure of the verticals? Well, by some measure, mx, that may depend on the point x. What I'm using here is, one can always find a family of measures mx in projective space such that this is true. Okay. In fact, it is if and only if. A measure belongs in this set if and only if it can be disintegrated in this way. And this, the statement that I'm using is called the Rochling theorem, theorem of Rochling. It's a non-trivial theorem, but it's a theorem in measure theory. If you have a measure in a product of two spaces, not too bad, that projects down to a certain measure mu, then this measure m can be disintegrated. You can find a family of measures such that this formula is true for every measurable d in m cross PR2. It is not important that this is projective space. Any compact metric space, for instance, would be okay. Okay, so if we want to exhibit M, if I want to exhibit M, it is sufficient to explain how I'm going to find these mx are called They are called the conditional probabilities of M. In my book on ergodic theory, you can find the proof of Rocklin's theorem. Okay? So, in order to explain which measure is that, I have to say what conditional, what are these MXs that I'm going to consider. Okay? But it's more or less obvious at this point, because I want this set to have full measure. I want this set to have full measure. Right? So this number, if I consider D to be this set, if I consider D to be this set, D has to have full measure. This has to be 1. Now, so the integral is equal to 1. But these numbers here are at most 1. So if I want the integral to be 1, I need for this we need that mx that appears in the integral has to be 1 for mu almost every x. These these are probability measures. Everything here is probability measure. Okay. So if the integral is 1, then, and this function here takes values at most 1, the only way the integral is 1 is if these numbers are 1 for almost every point. And in this case, D is just the graph. And when I take this D and intersect it with the vertical, I get this. Right? So I need that the set of V's such that V belongs to Vx2 has to be 1 for mu almost every point, for mu almost every x. However, in this case, this set here, since V2 is a line, is a one-dimensional subspace, this is a single point. This is just this point here. So my m of x has to be supported on a single point. This is just one point, because V2 is a line. Okay? So the conclusion here is in our setting, m of x has to be the Dirac mass on that point. I really don't know how to call that point. I'm going to call it Vx2. Or maybe, let's avoid confusion. Let's call this point C of x. Okay, C of x is this point here. It's the unique point in projective space. It's the same as Vx2, seen as an element of projective space. Okay, so the way we construct the invariant measure, it's sort of trivial once you think about it. The way we construct this invariant measure is by taking Dirac mass on each point and then multiplying that by mu, then integrating that by mu, as in this formula here. Okay? The proof of the theorem, in general, is not very different from that. The theorem is not very, it's a clever statement, very useful, but the proof is not very hard if you keep in mind this situation. Okay? Of course, I said that in general these conditional probabilities depend on x. If they don't, then that's because this measure m is the product of mu by some measure in projective space. But in a picture like this, clearly the Dirac mass depends on the point x. In general, it depends on the point. Okay. Questions? Okay, so let's see how the proof goes, but please keep this example in mind because it's basically, the proof is just a grown-up version of the same argument. One has to work a little bit more, but it's not very different. Okay, so, so let's prove the theorem. The first part is essentially the ergodic theorem. So if M is invariant and ergodic, then limit 1 over n sum phi pf to the power j x v exists and is constant and is equal to the integral of phi with respect to m by the ergodic theorem. This is mu for m almost every pair xv, and this is just the Birkhoff. Applied in the case where the measures are high. Okay. Now that's one little caution that we have to have. The ergodic theorem does say such a thing when the function phi is integrable. Okay. And so we have to come here and see if this function is integrable. And I'm just going to say that phi is integrable, just going to observe, integrable with respect to m, a measure that projects onto mu, if log plus of a and log minus of a, log plus of a inverse are integrable with respect to mu. And this is very simple. If you look at the expression of phi, you see that it is bounded by log of the norm from above and bounded by the log of the conorm from below. So it is in between. So this is a simple observation. And I didn't say it, but I always assume that. I always assume that log plus of A and log plus of A inverse are integral, are mu. Okay. So what is this? The left-hand side here. Limit 1 over n sum of phi calculated at fjx and then ajx of v now phi is given by this expression. So I have logarithm of the image minus logarithm of the vector. So if I apply the formula here, that gives logarithm of aj plus 1 of xv minus logarithm of ajxv. Of course, I could write logarithm of the quotients. And now I guess you understand why I decided to look at this expression here. This is nothing else but limit of, you have this telescopic cancellation, limit of 1 over n log of an of x v minus 1 over n log of v when you do this telescopic cancellation. And of course the last term is completely irrelevant because this is constant and it's divided by n, so ultimately this is 1 over n log of anx of v. Okay, I have done nothing up to this point except using the Birkhoff-ergodic theorem. And my conclusion is, what I get in this way is that what I proved so far is that limit 1 over n log of anxv is equal to the integral of phi dm for m almost every pair x v. Okay. Now I'm going to look at these sets. I'm going to look at the sets Vj equals, maybe I don't want to call them Vj. No, I don't. I want to call them. So here is a v. Now this is what we call lambda xv, the Lyapunov exponent associated to the vector v, except that when we defined this, it was a lim sup, and now we already know that it's a limit. But otherwise, this is just... So, the integral of phi dm has to be one of the lambda j's. It has to be one of the lambda j's because the lambda j's are the possible values for this limit. Simple as that. The Lyapunov exponents are all possible values for this limit. For almost all pairs, we get the same number, so this number has to be one of the lambda j's. And limit 1 and lambda x v is equal to this lambda j for every, for not every, for m almost every x v in m cross projective space. You see, it's a lot easier to understand than to explain because I'm not doing anything. I'm just playing with the definitions. So this has to be one of the lambda j's because lambda j's are all possible values of this, and that's all the values I get for lambda for almost every point. Now, we also know what is the relation between the point and lambda j. This means we have the flag. Let me remind you of the flag. And depending on the position of your vector with respect to this flag, you get a different Lyapunov exponent. So where do you get lambda j? You get lambda j if and only if v belongs to vxj minus vxj plus 1. Okay? To say that the Lyapunov exponent of v is lambda j is equivalent to saying that your vector is in between the jth and the j plus first subspace in the Ocelides flag. So now you read what is written there, and it is written that almost all points are here. So it is written that the set of points x, v, such that v is in the difference has full measure. Right? And so this set, which is a bit bigger, also has full measure. It's a little bit tricky to look at this proof because in the end it's just definitions. The only thing that is not a definition in this proof is the Birkhoff ergodic theorem. Otherwise, this construction is just using the definition of the Lyapunov exponents and the Ocellet's flag. Any questions about this? Yeah, that's right. That's right. That's right. But I don't really see how to. I mean, anything that you do for ergodic, you can somehow formulate in general by ergodic decomposition. However, it's not entirely clear what the statement would be here. It's kind of complicated to write down. Okay. Since every invariant measure can be decomposed into invariant ergodic measures, it's not really a restriction to assume ergodicity, but in this case, it helps in keeping the statement fairly simple. The exponents are constant, and the number of exponents is also constant, which is nice for us. So now we have to go and prove the converse. And you see, in order to prove the converse, we have to construct some invariant measure. And whenever you want to construct an invariant measure, the trick is always the same. I'm going to write down the trick here, then I'm going to erase it, and I'm going to do it properly. If you have a transformation, how do you construct a T invariant measure? The basic trick is always the same. Then you have to work harder or not so hard depending on the situation. You take to get a T invariant measure. You start with any measure. With any measure. New. You iterate this measure, Tj star of new. So just Tj star of new is the measure defined by Tj star of new of a set E is new of T minus J of E. So we just iterate this measure forwards. You would love to say that this converges to some mu. If that were the case, mu would probably be an invariant measure and you would be done. But in general, it doesn't converge. The one thing that you can say is that this sequence has some subsequence that converges. Because if you are in the right place at the right time, the space of measures is compact, then any sequence has a subsequence. But if you take a subsequence and the subsequence converges, it's not true in general that the limit is an invariant measure. If the sequence, all the sequence converges, it is true. But if it's just a subsequence, it's not true. So you do something a little bit more sophisticated. You take the sum, j from 0 to n minus 1, and you divide by n. So instead of taking the sequence of iterates, you take the Cesaro sequence associated. Okay? Usually, by compactness, by compactness of the space of probability measures, this sequence has some subsequence that converges. Some subsequence. And then mu is invariant. I'm not saying this is a proof. It's certainly not the general medicine to construct invariant measures, because usually you want more properties. But under rather general situations, this strategy works, and in all situations that I can think of, that's the strategy. You take any measure, you iterate and consider this average, and because you are considering the average, any accumulation point will be invariant. It's the fact that you divide by n here that helps. So that's the idea, the general idea for constructing an invariant measure. But of course, if you are going to do this in a particular case, you have to justify the steps. You have to prove compactness in order to be able to use this subsequence, and you have to check that indeed any accumulation point of the Cesaro averages is invariant. But this is one example of one situation where that strategy works. Now, we prove the converse now. So for the converse, I need a few lemmas that correspond to implementing that strategy. The first lemma says that the push forward from m mu to m mu that takes any measure and maps it to in our case, the transformation that we want to consider is the projective cocycle. Is well defined and continuous with respect to the weak star topology. Weak topology in the space of measures. Maybe I should remind you what the weak star topology is. I'm just checking my assumptions. Yeah. Okay. So let me, before proving this, let me remind you of what the weak star topology is. So if you have X, a metric space, and you consider the space of, we call M1 of X, is the space of all probability measures on X. the weak star topology in this space, so it's a topology in the space of probability measures, is defined as follows. So if you want to define a topology, you have to, for instance, say what means convergence of a sequence. And the definition is a sequence of measures converges to another measure by definition if and only if, and this is convergence in the weak star topology, if and only if you integrate a function with respect to mu n, these numbers, these integrals, converge to the integral of the same function with respect to mu. Okay. For any continuous bounded function phi from M to R. The fact that I include this condition that if phi is bounded guarantees that the integrals exist. Bounded functions are integrable. Continuous functions are measurable, and if they are bounded, they are necessarily integrable. So that's the definition. Two measures are closed in weak star topology if the integrals they give to continuous functions are closed. That's the idea. Measures are good for integrating functions. You say that two measures are closed if when you integrate functions they give numbers that are closed. If you don't like continuous functions and you prefer uniformly continuous functions, you can write uniformly here. It doesn't change anything. The definition doesn't change. If you don't like continuous functions but you like Lipschitz functions, then you can replace continuous by Lipschitz and the definition doesn't change either. Okay? So that's what we mean here. So I'm using in this statement this weak star topology is this weak star topology in the space M mu. Of course. For you to define a weak star topology, you need the ambient to be a metric space. And so here I'm always assuming, I didn't say it, I forgot to say, I'm always assuming that M is a metric space. This weak star topology has some nice features, nice properties. The first one is that it is always metrizable. It is metrizable. If M is separable, then M1, if X is separable, then M1 of X is separable. Separable means that there exists a countable dense subset. If X is complete, then this space is complete. And if X is compact, then this space is compact. Okay? All of this, if you want, you can find in my book on ergodic theory. Okay, so how do you prove this lemma? We want to prove that that it is well defined. What means well defined? Well, you start with a measure that projects down to mu. You want to know that the image projects down to mu. That the image is in this space. So first, we want to show that if pi star of mu of m is mu, then pi star of p f m is also mu. That's what it means well defined. If I start with a measure in this product that projects to mu, when I apply P of f, I get another measure here, P of f star m, and it still projects to mu. Now this is very easy. Maybe that doesn't look easy, but it's very easy. The reason is that P of f is a map from M cross PRD to PRD, to the same space. This is P of f, projective cocycle. Pi is the projection to the first coordinate, M. So if you do this here, and you look at what you get downstairs, well, you remember the formula for projective cocycle. So when you project, what you get is the dynamics in the first coordinates. What you get here is f. X goes to f of x. So and this diagram commutes. You take this, you apply pi, you get x. You apply f, you get f of x. If you go the other way, you apply first the projective cocycle, you get f of x, and then you project, you get f of x. Okay, so this diagram commutes, which means that pi composed with pf is f composed with pi. Okay? And then you just check that this implies pi star composed with pf star is equal to f star composed with pi star. This push forward in measures is functorial. And so in particular, the measure that we are interested in, which is pi star of pf star of m, is the same thing as f star of pi star of m, which is f star of mu, and then mu being invariant, this is just because mu is f invariant. Okay, so this proves what I wanted. Now I want to prove continuity. Well, continuity means that the function preserves converging sequences. So I want to prove, we want to show that if Mn converges to M, then Pf star of Mn converges to Pf star of M. Continuity in the weak star topology. This weak star. And I'm going to use the definition. If the integral of phi dmn converges to the integral of phi dm for any phi continuous and bounded, then integral of phi d, this is complicated to write, dpf star mn converges to the integral of phi d pf star of m. Maybe I should use a different letter here, psi, for any psi continuous and bounded. Okay, so this is what we want to prove. I'm going to give two proofs. Each one has some advantages and some disadvantages. The first one has the advantage that it is quick, and the disadvantage that it is false. The second one has the opposite disadvantage. It is a bit longer, but it's correct. So first proof. Of course, the fun is to discover where the proof is wrong. Given any continuous bounded proof function I look at this, okay. Now this is the same thing as C composed with PF dmn. In a sense, that this is the definition of push forward. What the push forward of a measure means is essentially this. Then I take this to be phi, and I use the assumption. The assumption tells me that this converges to phi integral with respect to m, and then by definition this is end of the first proof. It should be easy to find out where the mistake is. Where is the mistake? I'm not assuming, I don't want to assume that this map is continuous. I could, but I don't want to. Because there are examples, interesting examples, where it is not continuous. For instance, sometimes I want to work with functions, with transformations that are not continuous. Or with matrix functions that are not continuous. And of course, if I fix x and I let vary v, then as a function of v, this is continuous because I'm talking of the action of a matrix in projective space, and that's very nice. Okay, but I don't want to assume that the dependence on x is also continuous. So this is wrong because phi is not necessarily continuous. Now, I forget which book it is, but I think it is the book of Halmos on measure theory, I think, where he says that measure theory is that part of mathematics where you learn that all measurable sets are open, all measurable functions are continuous, and all pointwise converging sequences converge uniformly. Okay, up to a little set, and that's the kind of trick that you use. It's a good rule to keep in mind. If you are able to prove it for continuous, then perhaps with 95% more work, you can do it for measurable. So that's the trick I'm going to use here. Well, let's correct this proof. So, given any epsilon, there exists closed subsets L there exists a compact K contained in M. Now, this is called the losing theorem. Lusin's theorem. And in fact, there are two different versions of Lusin's theorem. One where you assume that your space is just a metric space and you get a closed set. And a somewhat more specialized version where you assume that your space is separable and complete, and then you can take a compact subset. I'm not sure why I wanted a compact subset at this point, but anyway, I'm going to stick to that setup. Yeah. Okay. At the beginning of the chapter, I say we always take M to be a separable, complete metric space, and this is one of the places where that is useful. There exists a compact subset such that the complement has small measure, and F and A are continuous. Okay, so that's why every measurable function is a continuous function up to so this is f restricted to k, and this is a restricted to k, and so f restricted to k cross PR d is continuous. Okay, so you exclude a small fraction of your space. This is k complement. You exclude a small set, and outside our map is continuous. So now I can do that properly. I want to estimate the difference between phi composed with pf dmn minus, I want to estimate this, minus phi composed with pf. This is pf dm. Okay, and I want to show that the difference is small if n is large. So I write this, I separate according to, one has to be careful here. It's continuous, yeah. So let's give credit to Lucine, and we need a companion theorem. We need a companion theorem, which is the theorem, the extension theorem of Tietz. The extension theorem of Tietz says, so this was psi, right? Before I do this, so this function is continuous. And so, psi composed with this, restricted to k, is continuous. Okay, so my problem was that this composition is not continuous in general, but I've shown that we can always assume that it is continuous on 99% of your space. Okay. Now, Tietz, the theorem of Tietz, says that there exists some function which is continuous. Such that, first of all, phi is continuous. Secondly, phi is an extension of that function. That's why this is called the extension theorem. And third, phi is less or equal, and the supremum of phi is less or equal than the supremum of psi composed with pf. This is a very nice, very handy theorem. It says if you have a continuous function on some compact subset of your space, then you can extend this to a continuous function on the whole space without increasing the supremum. Of course, this is less or equal than the supremum of psi. And the reason I'm interested in that is that I assume that psi is bounded, and in this way I'm sure that phi is bounded as well. Okay? So now I can raise the wrong proof. So now let's calculate psi composed of pf dmn minus psi composed with pf dm. Of course, we are going to split into two parts, inside k and outside k. So this is less or equal than the integral of phi dmn phi dm, and then I have to compensate for the difference between the two. So plus integral of psi psi composed with pf dmn minus psi composed with pf dm, and this is integrated on the complement I'm being very pessimistic here, but it's okay. Okay. Really being very pessimistic. Taking the place where the two functions may differ, I'm just adding up. Okay. Now let's see what this gives. Integral of phi dmn minus integral of phi dm. This I'm not going to change. And now let's look at this. I'm going to be very brutal here. I'm going to bound everything by the sum. So what about this? This function is less than the supremum of psi, and the domain of integration has measure. What is the measure of the domain of integration? Well, the measure of kc times p rd, the measure of this region here, since m projects to mu, is the same as the measure of kc, which is small. Okay? So this integral here is bounded by epsilon times supremum of psi. That's true for mn, but that's true also for m, because all these measures project down to mu. This is true for m, but it's also true for mn, because they are all in this space. So this integral is smaller than epsilon times supremum of psi, this is also smaller. The supremum of phi is less or equal than the supremum of psi, so the same calculation works here, and the same calculation works here. So, plus 4. Okay. So, when I make n go to infinity, the limit, well, I don't know if the limit exists, but I'm taking the lim sup. The lim sup of this is less or equal than this limit plus 4 epsilon times the supremum of psi. Now, this limit is 0 because phi is a continuous function and mn is converging to m. So less or equal than 0 plus 4 epsilon supremum of psi. Okay? And now if I make epsilon go to 0, now I make epsilon go to 0. We get that this limit is equal to 0, which is what we wanted to prove. Okay? So you see, it really doesn't hurt to think of that everything is continuous here, because we can reduce essentially to that case combining leucine and teats. And this has nothing to do with our particular situation. It's very general tools. So why did I prove this? You have to keep in mind this basic strategy that I well, maybe I explain that after I state the next theorem, next lemma. The next lemma says that M mu is compact in the following sense. Every sequence has some convergent subsequence. This is the compactness that I said we need for using this strategy. Okay, so let me say something about notation. This property here is usually not called compactness. It's called sequential compactness. Sequentially compact. For metric spaces, it's just the same as compactness. In fact, for any topological space that has a countable basis of neighborhoods, this is the same thing as compactness. In general, is not the same thing. This space is metric, is metrizable, but I don't want to prove that. I don't need to prove that, and I don't want to prove that. So it's okay to call this compactness, but it's perhaps more reassuring to call it sequential compactness. Although, in fact, we have both. We didn't. We are proving this for any map of this form. These are exactly the assumptions that we used. So we use that it is a skew product, the first part of the argument, to prove that it takes a measure that projects to mu into a measure that projects to mu. That's why this diagram commuted. So we use that it is a skew product. And we use that this depends continuously on V, because I said once you know that F and X and A depend continuously, F and A depend continuously on X, then your map is continuous. I never had to worry with continuity on V. So these are exactly what I've said. And no, we don't need this to be the projective space. Any compact metric space would do here. Okay. Now I'm going to justify that this is sequentially compact, and the proof is basically it's essentially an application of a general fact. It's called the theorem of Prokhorov. The theorem of Prokhorov says this is Prohorov's theorem. A family of measures, of probability measures, is sequentially compact if and only if it is tight. That is, family M of probability measures is sequentially compact if and only if it is tight, which means that for any epsilon there exists some compact K such that nu of K complement is less than epsilon for every nu in your family. Now this is a little bit confusing because I said something that looks very similar just a few minutes ago. Lusin's theorem says something of this type. In fact, an even more elementary theorem says that if you have any Borel measure on complete separable metric space, then there, given any epsilon, there exists a compact set whose complement has measure less than epsilon. For any measure on a complete separable metric space is tight. Okay? But that's a statement for one measure. then this is a definition for a family of measures. A family of measures is tight if you can find the compact that is good for all of the measures in the family. Okay? The point here is that the same compact set, same K for every nu. This is what is interesting in the okay. So what this is saying is that you choose your epsilon, you can find a big compact set such that all of the measures are essentially inside this compact set. All of them, what they have outside is small mass, uniformly small. Okay. For example, if your space is compact, this is automatic. Because then you can take K equal the whole space. So this is the theorem of Prokhorov. So what this helps us in is that we only have to prove check that M of mu is tight. Right? You take M to be M of mu. We only have to prove that M of mu is tight. And we already know that. For any given epsilon, take L compact such that mu of L complement is less than epsilon. For one mu, that's general. On any metric space separable complete, that's general. For one measure. Then take K equals L cross PRD. Right? Then M of K complement is equal to mu of L complement is less than epsilon for every M in M of mu. That is, this compact set is good for all of the measures in M of mu. So tightness is proven. Okay? Remember the picture. We have this picture. If you remove a little L complement here, and then you remove what is above it in the projection, what is outside is a compact set. It's a product of two compact sets, so it's compact, and the measure is the same because M projects down to mu. Okay? So this proves lemma 2. And now I can find, with these two lemmas, we can construct PF invariant measures. The way I'm going to do it right now, they will not satisfy star yet. I will have to be a little bit more careful. Okay? But I want to finish the cycle that I started when I said what the strategy is. Let's first construct some PF invariant measure. So what is the trick? Take any measure that projects down to mu. Any one. Of course, you could ask, is there any measure that projects down to mu? But that's a very silly question. You are not going to ask that. Because, yeah, of course, you can take mu times anything, any measure here, and if you take a trivial product and you project down to mu, you get mu. You project down on the first coordinate. So getting some measure, not necessarily invariant, that projects down to mu is very easy. Take any one. Then consider the sequence mn equals 1 over n sum as I said, you take these limits, these averages. First of all, mn projects down to mu for all n. Why is that? Because if you take, by lemma 1, if you take a measure that is in m of mu, all the iterates are also in m of mu, and then if you take the average, that remains in m of mu. Okay? It's basically by lemma 1. What else? So there exists a subsequence such that 1 over n k, such that mnk converges to some m. And that's by lemma 2. So now I'm giving you the ingredients of this strategy to construct invariant measures by lemma 2. Okay? Pf star of m is Pf star of the limit of m and k, which is equal to the limit of Pf star of m and k. So why am I allowed to switch to switch the limit with Pf? Because Pf is continuous. This is by lemma 1. What else? Well, let's look at this. What is the limit k Pf star of m and k? Well, it's the limit of 1 over nk Pf star of Pf star of 1 over nk sum right. This 1 over nk is not a problem. We can, it commutes with, it's just a constant. You can take it out. And then I have pf star of the sum. The sum you can also take out. And you get the sum of pf star of pf star j m n k j from 0 to nk minus 1. Okay. Well, if you are familiar with working with these push forwards, all I'm saying is obvious. If you're not familiar, you have to check that these operators commute with constants and sums, and finite sum. Good. Now, this I can put together is the same thing as pf star to the j plus 1. Okay? So this I can replace by pf star j plus 1 m n k. But I can do better than that. I can say that this sum is the sum j from 1 to nk of pf star j m n k. Instead of writing j plus 1 here, I prefer to displace the variable. So what I have so far is that the limit of pf star of m and k is the limit of 1 over nk sum j from 1 to nk pf star j of m0. I think I made a mistake here. This is m0. Okay. And now, and this is the point where you see the advantage of considering these averages. This is the same thing as 1 over k sum j from 0 to nk minus 1 plus the last term minus the first term. First term is j equals 0 is just m0. Okay. Now, this, by definition, converges to m. Okay. Converges to m. This is easy. You have a probability measure, you divide by nk, and you make k go to infinity, nk goes to infinity, this converges to 0. Always meaning that if you take integrals of continuous functions, that will converge to 0, continuous bounded functions. And this also converges to 0. For the same reason, really, because this is a probability. Okay? This is not a very rigorous way of saying it, but you write down the integrals and so on, and you check that what I'm saying is correct. Both are probability measures, this one and this one. You are divided by a variable that goes to infinity, this goes to zero, to the zero measure. So, conclusion. Conclusion. Pf star m so from 4 and 5 from 3 and 4 Pf star m equals this limit, and this limit is equal to m. Okay? In other words, m is Pf star invariant. Is Pf invariant. Is the image of its push forward. Okay. This is not the end of the proof, because I want more properties for m. That we will do next time on Tuesday. I won't be here on Monday. On Tuesday, we'll do that. And what we'll have to do is to choose m0 carefully, so that the measure that I get in this way will have the properties in the statement. Okay? Okay, questions?